Hi, we're going to go through all the Stokes Theorem questions. I'll be very surprised if I get all these right on my first try. See if you can spot any cuts I make in the video if I don't point them out myself. So we know that Stokes Theorem generally states that the surface integral of the curl of f ds is equal to the line integral f dot dr. And about half the time you'll be using this guy, and about half the time you'll be using this guy. So really it's just picking between which of the two is easier to use in either case. So if we take a look at this first problem, we are looking at a section of a paraboloid here, and we see that it's a downward facing paraboloid from z equals 4 to z equals 0. So we can kind of graph this thing out. It's going to kind of come down like that. And we have some choices here. We can either parametrize this surface and try to solve through either of our methods, or if they're nice to us, we can do it another way. So we see that f is relatively simple. We're not dealing with anything that looks too crazy in there. So let's try taking the curl, see where that leads us. So the curl of f we know is del cross f, and we can set that up as partial x, partial y, partial z crossed with negative y, x, z. And when we compute this cross product, we're going to get 0, 0, and 2. So that's interesting. That's looking pretty simplified. Generally, if you get something that easy after this step, you're going down the right path, and that's a good thing. So we know we have curl of f, and then we know that we can change our double integral over the surface ds because we have because we're dealing with a force field vector in here. We can change this to a double integral over the xy projection of this graph, dotted with the normal vector dA. And in our case, our normal vector is just going to be made out of, let's see, normal vector equals negative zx, negative zy, comma 1, because they say that they want an upward pointing normal, so our z component needs to be upward pointing. And this problem is actually probably the nicest Stokes Theorem question you could possibly come by, because we don't even need to compute these partial derivatives because they're just going to get dotted with zeros. So really, this dot product, no matter what zx and zy are, this dot product is going to be 2. So now we have the double integral over the xy projection of this area, because you remember Stokes' theorem, it is not dependent on what surface we have in here. So we could just take the path around the intersection with the z-axis, and that will give us our answer. So we can set up a nice little polar integral to do this. What we're really looking at is a circle of radius 2. You can kind of see that if z is 0, then we can put negative 4. Well, we can move 4 to the other side and get negative 4 equals negative x squared minus y squared. And rearranging everything, we get r squared equals 4 and r equals 2. So there's our circle of radius 2, and there's no bound on theta, so we can set this up as the double integral of 2 dr d theta, putting an r in here, from 0 to 2 dr, and from 0 to 2 pi d theta, and we're not dependent on theta, so we can get rid of 2 pi, get rid of d theta, move everything over, so, oops, we grabbed a little bit of the y, move everything over so we have a little bit more space, and multiply the outside by 2 pi, and removing that d theta. So now it's just a matter of integrating, we're going to get r squared on 0 to 2, which is 4 times 2 pi that we had sitting out here, and 8 pi is our answer. Okay, let S be the semi-ellipsoid oriented so that the normal is upward pointing. And we are given F here, and we're told to use Stokes Theorem to find this. But in this case, we will try to set up our curl, partial x, partial y, partial z, x squared, y squared, z squared tan xy. This is horrific to try to take a cross product with, because you'll see we'll get a secant squared, we'll get another secant squared in here. It's overall it's going to be absolutely terrible if we try to go down that route, and so we need to do something else. So instead, we can note that this semi-ellipsoid is in the form z equals, which is always nice because that will let us find our normal vector quite easily. And let's just do that to start off with. So zx is going to be negative 2x over root 1 minus x squared minus y squared, and zy is going to be negative 2y over root 1 minus x squared minus y squared. There we go. And so we can form our whole normal vector with this guy, and we want an upward pointing normal vector. So we notice that we have to have the negative zx and negative zy. So these signs actually get flipped. And if I can avoid erasing everything else like I just did, 1. There we go. So there's our normal vector, and that's looking a little bit scary. But in the end, it's actually not too bad. We've kind of gone down a rabbit hole by making our normal vector, because really what we can do to solve this much easier is to remember that our double integral over S curl F dot n ds, or sorry, well, this is really not there. Well, actually it is, dot n ds. This is equal to the integral over the curve F dot dr. And so if we want to solve this, we need an r, and since we know that Stokes theorem, all we really need is the path that runs around some bounding path for the surface. In this case, we're dealing with a semi-ellipsoid, they say, so it'll be kind of bulging up in the middle, but we can take a path from this to make our r. So in order to do that, let's make z into a constant up here. So let's make z equal to, why not 0? So 0 equals 2 root 1 minus x squared minus y squared. Divide by 2, square everything, move 1 over, and we can rearrange everything to x squared plus y squared equals 1, which is a parametrization that we're much happier with. We can parametrize this thing. R, oh, that's an F. R of t is equal to cosine of t, sine of t, and what's our z equal to? Well, z is 0 in this case. And so making a little bit of extra space for ourselves, we can now take this r, and really we're rearranging this f dot dr to f of r of t times r prime of t dt. And so in order to fill in these blanks, we need an r prime of t. Let's find that. Whoops. R prime of t is going to be negative sine t cosine t 0. And f of r of t is going to be, well, the I component is just x squared, so cosine squared t, and then the y component is going to be sine squared t. And what's nice is because we've made a path such that z is 0, this entire really disgusting section gets canceled out because z is 0, so nothing in that tangent matters, and that component is 0. So taking our dot product with r prime of t and f of r of t, we can set up our whole integral that we're going to need to solve. This is going to be from 0 to 2 pi because we need the entire pathway around the semi-ellipsoid. Well, it's really this circle that we've made in 2 dimensions. But this is going to work out to negative sine squared times cosine squared, which is negative sine t cosine squared t plus sine squared t cosine t. And we'll tack a little dt on the end over there. Okay, so making a little bit more room, we can split this integral up into 2 smaller integrals and do u substitution on each of them individually. So the integral from 0 to 2 pi of negative sine t cosine squared t, we can set u equal to cosine t and du to sine, well, negative sine t dt. And this integral will become the integral from 1 to 1 of u squared du. And when we evaluate this, and it's kind of hinted by our bounds being the same, this will evaluate to 0. And as it turns out, if we evaluate this second integral that we've left in here, if we do our u substitution with u equal to, say, sine of t, we will end up with, rearranging our bounds, we will get 0 and 0, and that integral will also be 0. And so overall, this is just 0. I kind of left in this earlier stuff with the normal vector and everything because this is what you will actually be doing in exams. You'll go down the wrong road and then realize it was the wrong road and have to kind of pull yourself back out and realize that there's a better way to do the question, and also because I legitimately wasn't sure what to do, and it's good practice for me to remember how to pull myself out of those holes. Okay, we are given a parametrization of a curve, the bounds on t for that curve, and we're told that it's the intersection of this cylinder with this plane, and we're also given our force field. So now they're giving us f dot dr, and just like the last example, it's a good hint if they give you that equation for Stokes that really it would be easier to use the other one. And we see that because the curl of f is actually going to get rid of all of this trig garbage. So let's set that up. Partial x, partial y, partial z, y plus sine x, z plus sine y, and x plus cosine z. And when we do this cross product, we will get -1, -1, and -1. So there's our curl of f, and anytime you're seeing constants like this, you know it's a generally good clue that you're going down the right path. And then, okay, what is our normal vector? Well, we're looking at the intersection of a cylinder with a plane, and this plane is just, it's cutting through this cylinder at some point. And what is a plane defined by? It gets very convenient very fast because the plane's normal vector is its definition, like its coefficients. So this normal vector will be 1, 1, 1. And that's perfect because we can take that dot product and then set up a double integral over the 2D projection of this intersection over here, and we'll be done. We're dotting that with 1, 1, 1, which will give us -3, setting up our integral from 0 to 1, because the radius of our cylinder is 1, and from 0 to 2 pi, r dr dt, d theta. And of course, like usual, we're not bounded on theta at all. We can put a 2 pi there. And -3/2 r squared on 0 to 1 will be -3/2 times 2 pi is -3 pi. Okay, let S be part of the circular paraboloid below the plane z equals 4 with upward orientation. And then let's just write our f out because the I is 0, so we got to have that down somewhere to remember it. It's going to be 0, comma, xz, comma, yz. And now we're computing Stokes Theorem over here. And if I remember correctly, curl f dot n ds is actually the better way to go about this. So let's try it. Could be very wrong. And actually looking closer, I'm almost definitely wrong because they're giving us a hint with some trig functions in there. So that's a good hint that, we should be parametrizing something. So let's parametrize something. Let's see, we're looking at this paraboloid below the plane z equals 4. Sure. Okay, and that's going to be the upward opening paraboloid, kind of going up like that, and it's cut by z equals 4, and when it's cut, it will be a circle of radius 2, and if you want to 2, 2, -2, -2. And if you really want to convince yourself of that, just set z equal to 4. 4 equals r squared, r equals 2. Okay, so making a little bit of progress here. We might as well just set up our parametrization and see if we get something nice. Well, let's make sure we remember this is f. So our r of t, if we're looking at this kind of top path that our paraboloid is cut by, well, that's just going to be 2 cosine t, 2 sine t, and 4 for our z value. And then we know we'll need our r prime of t because we're going to be dealing with an f dot dr in the end. So we need our dr, which will be -2 sine t, 2 cosine t, and 0. Okay, perfect. At this point, we just need to put everything together, and that involves finding f of r of t, which is going to be 0, comma xz, which is 8 cosine t, and yz, which is 8 sine t. There we go. And all we have to do now is set up our integral from 0 to 2 pi of f of r of t dotted with r prime of t, which you see when we do this dot product, we're going to get 0 here, 0 here, and 16 cosine squared t there. Cosine squared t dt. And I wish they would do this more where you're kind of being benefited by setting everything up. They don't make you, this would be relatively easy to do. We could use a half angle a double angle identity to replace cosine squared t with 1/2 plus cosine 2t over 2. That's the worst cosine 2t I've ever written. But we could do that, but they're being nice here. They're telling us that this integral is equal to pi. We're dealing with 16 times that integral, so we're ending up at 16 pi. Okay, I'm restarting this question just because I went down the wrong rabbit hole. It turns out the trend that we were seeing earlier does continue, where they're telling us to use curl f.ds but really that's a very good hint that you should be using f.dr. So all we need to do for this one, it ends up being a lot of work doing curl FDS, and I'm pretty sure I made some algebra mistakes somewhere and that it would have led to a correct solution if I had just been a little more attentive. But all we need for this, we know, is an R of t. We're dealing with the sphere above the xy planes and the sphere of radius 2. And so really, we can use the path around this hemisphere, which is going to also have a radius of 2. So r of t is going to be 2 cosine t, 2 sine t, 0, and r prime of t is going to be negative 2 sine t, 2 cosine t, 0. And then all we need to find is f of r of t, which becomes very nice because this xyz gets canceled out, as you'll see, because z is equal to 0 in both cases up here. So f of r of t is going to be negative y, so negative 2 sine t times, not times, but our y component is going to be 2 cosine t, and then our z component is going to be 0. So now r prime of t dotted with f of r of t is going to give us 4 sine squared t plus 4 cosine squared t. So we know that this simplifies down to 4, and we know that the integral that we're taking, this is a line integral, and we need to go all the way around this, so it's going to be from 0 to 2 pi dt, which evaluates to 8 pi. And finally, using Stokes Theorem to evaluate this integral where C is the intersection of, again, a cylinder and a plane. And we know that the normal vector to this plane will be 1, 1, 1. And we see that C is oriented counterclockwise when viewed from above, which is good. It means we don't have to flip a sign from what we would normally do. We see that this is actually f.dr that they just expanded up here, which we can combine back up into itself to form f, the force vector f, which is y, comma z, comma x. And so this, it seems like the trend holds for all of them, where they tell you to use f.dr. Really what that means is use curl f.nds. So let's curl this guy. This is going to be partial, partial x, partial, partial y, partial, partial z, y, z, x. And when we curl, we will get negative 1, negative 1, negative 1. Okay, that looks good. We already know our normal vector is 1, 1, 1. Dot those together. We will get negative 3. And we know that this is a line integral, and we need to go around this little circular area that is the intersection of our cylinder and plane. We need to go around this circular area once. So from 0 to 2 pi dt, and that will give us negative 6 pi. And we're done. Let's see, I think the total number of cuts in this video will be 3. We'll see how well I can hide them. But let me know if any of that was unclear. This is actually amazing practice for me because I really didn't put 2 and 2 together until I did all these in one shot. That it really is, at least, there's a very good chance if you see curl f.nds, it means, you know, this question is easier with f.dr, and the other way, if you see f.dr, it means use curl f.nds.